Well, thank you, everybody. I'm Jonathan Case and part of the NASA Sports Center at Marshall Space Flight Center. Be switching employers coming up this month to University of Alabama. And I'm going to talk to you about NL-3 development as a NASA multi-center effort. So let me first start by asking in the room, how many people are familiar with NL-2? And how many people have used the data or are actively using it? So yeah, probably at least say 25% of the audience is familiar and or using the data. So we're going to talk about making that revolutionary leap to the next generation of NL-DAS, the North America Land Data Assimilation System. So let me first start my talk by talking about the complementary nature of different data sources for of soil moisture. So Ford Inquiring 2019 described the utility of the complementary nature of in situ, remote sensing, and models as sources of soil moisture. So in situ sensors, that's predominantly the focus here. They provide the most accurate and calibrated measurements, but they have pretty sparse spatial coverage. Meanwhile, remote sensing platforms can provide a broader spatial coverage, but they have more limited temporal revisits, maybe twice a day if you're lucky, and they're relatively coarse resolution, 9 to 36 kilometers for SMAP, and they require complicated soil moisture retrieval algorithms. And another limitation is that they tend to be able to observe only that top surface level, maybe 0 to 5 centimeters. Meanwhile, land surface models, they can provide perhaps a more optimal spatial and temporal coverage, depending on how your model is set up to run. But going into the model, there's a variety of assumptions about parameter specification, the assumptions of physics, processes in the model. And of course, depending on how extensive your domain is, you have computational requirements can be quite substantial. So there really is no one size fits all solution, but if you use all three sources, that can really be complementary for, especially for stakeholders making decisions about drought and pluvial monitoring. So the North America Land Data Assimilation System, NL-DAS, has been widely used as a land modeling system operational at NOAA for well over a decade. The unique users have been growing in recent years. We look at the chart here in the recent few years, that's only indicating the people who are pulling the data off of the NASA server. There's also those who directly acquire the data from NOAA. And there's a whole variety of stakeholders and science groups that use and access the data. As we saw here in the room, we probably have a couple dozen or more users of NL-2 data. So introducing NL-DAS Phase 3. This is, as I alluded to, a NASA multi-center development, Goddard, Marshall, and JPL. And I'm going to be highlighting diagrammatically some of the key features of NL-3, and in red, you're going to see some of the improvements over the current NL-2. So we're going to run a more sophisticated land surface model, NOAA MP, that's NOAA with multiple physics. We have a variety of blended meteorological inputs that are downscaled at the same resolution as you'll see proposed for the model itself, 1 kilometer grid spacing. And we're going to be conducting data assimilation of a variety of remote sensing variables, soil moisture, snow, terrestrial water, and vegetation. And we will have high resolution outputs of water, energy, carbon fluxes over a very large, much larger domain than NL-2 currently. And I think some of the real bread and butter is going to be in this box that's partially covered by Peter Gogol talking, but we're going to be really focusing on data accessibility, the utility of generating and using derived products more readily in a cloud environment, and really keying in on data that's readily accessible to the stakeholder. So at the core of NL-3 is the NASA Land Information System, the LIS. And the LIS has the ability to run multiple land surface models, NOAA, NOAA-MP, VIC, among others. And we're selecting the use of NOAA-MP in this case. And we'll be using a state-of-the-art river routing model, HIMAP, in order to generate stream flow and stream gauge height information at gauge sensors. And I have the websites listed there for the Land Information System page, as well as the GitHub if you're interested in acquiring the LIS framework. So a couple of slides on the NL-2 versus NL-3 comparison. So what we're seeing here is the full North America domain for NL-3, and then the red rectangle here is the current NL-2 outline. So NL-2 is run at 1/8 of a degree, or about 14-kilometer resolution, covering predominantly the continental US and the immediate adjacent southern Canada and northern Mexico. But it cuts off, it does not include the Caribbean. And there's about 76,000 land points. So NL-3 will be an order of magnitude leap in the resolution down to approximately 1 kilometer, covering full North America, which includes the entire Caribbean. So this could be a good prospective data set for the Puerto Rico talk on landslide mitigation that we saw, and as well as Alaska and Hawaii. Now, with that expansion in both resolution and coverage, the number of land points leaps to over 27 million. So there's a dramatic increase in the computational requirements as a result. So therefore, we're starting with just running one land service model initially, that's NOAA-MP. So another comparison table summarizing the various attributes. So we talked about the first couple of rows. The latency is another issue that the stakeholders have provided inputs. They want reduced latency of the data. So we're going to go from 4 days latency with NL-2 to about 7 hours latency in the real-time configuration of NL-3. And at the core of NL-3 forcing is downscaled MERA-2 reanalyses, but there's also a sophisticated precipitation assimilation using various global data sets and calibrations. So that will provide a better depiction of global precipitation scaled down to North America. And as I alluded to, we're going to start with just the one land service model initially, and then we'll see where future funding takes us if we can expand to additional land service models. We're going to put the DA back into NL-2 with data assimilation, as I mentioned. And we're going to have a forecasting component that will be rolled out next year that we're going to develop, where we're looking at 2 to 4 week ensemble forecasts. So putting the DA back into NL-DAS, that's going to help resolve the combined natural and human impacts on the water and energy cycles. And I want to emphasize the fact that we've built on previous joint efforts with NOAA to emphasize, what does the stakeholder community really need in terms of a modern land service model with groundwater and prognostic vegetation, reduced latency, making NL-DAS truly North American with the coverage of Alaska, Hawaii, and the Caribbean and Puerto Rico, and improved forcing data sets and finer spatial scales. And with NASA Marshall's role, I'm part of the NASA Sports Center at Huntsville, Alabama, and we've had a 20-year proven paradigm of research to operations. So we're going to follow that paradigm, such as our prototype system, the Sport Land Information System, that we've been running for about 10 years. So here's a summary table of the various stakeholder engagements and their applications. And you can see we are covering the gamut of drought, water resources, agriculture, even fire management. We've done some studies on looking at soil moisture trends for lightning-initiated wildfires. NLDAS-3 will enable us to expand analyses to include Canada and Alaska, and wildfires are becoming increasingly important in those areas. So for the near real-time NLDAS-3, we ask the question, what do stakeholders need? So it's a user-centric design with low latency, easy to use output formats, and a flexibility to use the data to mask and generate statistics and useful information that could be readily digested. So some enhanced product ideas that are being co-developed for NLDAS-3, we're looking to implement the Soil Moisture Volatility Index. If any of you are familiar with that, it's a soil moisture type of metric that is designed to examine the potential for flash drought onset. And we are looking at the combined drought indicators at that link there. Texas A&M, Dr. Nielsen Gammons developed a precipitation fingerprint plot. So if you query the precipitation forcing, and you can look at 6-month to 5-year drought trends in that case, based on precipitation. And I've emphasized the layered data format because GIS is important to a number of stakeholders. And then other ways to query the data to generate statistics and really slice and dice the data. So getting into the forecast component, which we're expected to develop for next year. Currently, the sport land information solution generates 14-day forecast percentiles, but it's single deterministic runoff of the GFS forecast precipes predictions. So for NLDAS-3, what we're envisioning are 14 to 30-day ensemble forecasts to help bridge the gap from short-term forecasting to subseasonal to seasonal decision-making, and will provide deterministic and ensemble outputs. In the forecast ensemble proposal, we're talking about looking at things like the daily spread of the LSM, the land service model solutions, driven by either GEFS or the European model ensemble. And probably important metrics that you could look at would be to say that, for example, the probability of soil moisture falling below or rising above key threshold percentiles. I think that would be very meaningful for examining flash drought onset potential. So the estimated timeline for rolling out NLDAS-3, we're currently in the beta version of the 1 kilometer forcing, and we are generating the forcing variables, precipitation, downward radiation, and that's going to be hosted on a cloud server. And by later this summer and into the fall, we're going to run an open loop, which will be the archival period from 2001 to present, but without data assimilation. And then we'll do the full data assimilation run after the open loop is completed. And then finally, next year, we'll develop the NLDAS-3 forecasting strategy. So with that, here's a couple of links. The one on your left is a link to the sport list archives. We now have 1981 to present archives of the sport list climatology and percentiles and soil moisture information. And then the NLDAS-3 project page is at your right. And that has links to all the workshop content and slides that we've done with our stakeholders so far. Thank you.
Yeah, so I definitely have been a user of NLDAS-2 for a long time. I'm also a user of the NASA Western NLDAS, which is like the downscale 1 kilometer product with the idea that, you know, our region is complex in the Western US. Let's try to get a higher resolution. With NLDAS-3 coming out at 1 kilometer resolution, is there any reason why you recommend either still using Western LDAS for some applications, or do you think at that point it might be best to just fully switch over to NLS three?
Yeah, so, yeah, I'm actually not sure about the transition plan for WLDAS. Probably be similar to with our sport list, we'll probably continue running it for at least a year. But I think the personnel at Goddard Space Flight Center manage the Western LDAS, so I'll probably need to direct that question to our colleagues at Goddard and see what their plans are for continuing the Western LDAS. Or it could be that there'll be an intercomparison between NLDAS 3 to see how well they intercompare.
Thanks.
We have a question. Yeah, thanks. I'm with the Bureau of Land Management, Department of Interior, and I noticed that you had your own river routing model incorporated in NLPA. And I was just curious about interoperability with USGS's hydrologic network, 3D, or HD, and I don't know, I recognize that it's a North American scale. Thus, you're looking for the scale river networks, but I was curious about your thoughts about the potential for interoperability with in the Commons by the last river networks. Next.
That's a good question. I'm not the river routing expert, but there are two algorithms available in the land information system, and HIMAP, I believe, is the latest and greatest one that they have implemented. But yeah, I'll have to direct that question to our river routing expert to see how they plan to intercompare or work with USGS and their routing algorithms as well. Thanks for the question.
We have one last time.
Hi, so I have a question about the for the solution, with the data being RD or 3RD or DAB or all the resolutions, and other question was about land use change. Is that taken into account this item for the?
Yeah, so for the first question, because of the large data files, we're actually going to have daily averages for the historical period. The real-time solution, we plan on having hourly information. So, but that will have a more limited availability for near real-time applications. And I didn't quite catch the second question fully.
Land use change every time.
Okay, land, are we going to incorporate land use change information into the analyses? That's not initially on our scope right now, but that is an excellent point to bring about, that you could look into running the historical analyses with changes of the land use cover over year after year, because I believe MODIS has a database where they have annually changing land use cover. So that's actually an excellent suggestion. So that's something I'll definitely relay back to the team, and we can have a discussion about that.